Welcome to our deep dive into the mathematical foundations of XGBoost. XGBoost, short for extreme gradient boosting, is one of the most popular and powerful machine learning algorithms for tabular data. It's an ensemble method, which means it combines many simple models, called weak learners, to create a single, highly accurate and robust predictive model. In XGBoost, these weak learners are decision trees. In this guide, we'll peel back the layers and derive the core equations that make XGBoost so effective, from first principles. First, let's define our model. The prediction for a single data point, xi, is the sum of the predictions from k different decision trees. Here, fk represents the kth decision tree. To train this model, we need to define a goal. This is done using an objective function, which we want to minimize. The objective function in XGBoost has two main components, a loss function and a regularization term. The first term is the loss function, L, which measures the difference between the true labels, yi, and our predictions, y hat I. A common choice is squared error. The second term is the regularization term, omega. This is a critical innovation in XGBoost. It penalizes the complexity of the trees to prevent the model from overfitting to the training data. Training all k trees at once is computationally intractable. Instead, XGBoost uses a clever strategy called additive training. We build the model one tree at a time. Let's say y hat I at step t-1 is the prediction from the first t-1 trees. To get the prediction at step t, we simply add a new tree ft to our existing model. Our goal at each step t is to find a specific tree ft that minimizes our overall objective function. So, let's write the objective function for step t. We substitute our new prediction, y hat I at step t, into the general objective function. We can split the regularization term. The sum up to t-1 is a constant at step t because those trees are already built and fixed. This objective function is still complex because the new tree ft is inside the loss function L. To solve this, XGBoost uses a brilliant mathematical trick, a second-order Taylor approximation. Recall that a Taylor series approximates a function around a point. For a function f of x, the approximation around point A is given by this formula. Let's rewrite this for a small change, delta x added to x, so we are approximating f of x plus delta x. Now, let's map this to our objective function. Our function f is the loss L. Our point x is the prediction from the previous step, y hat at t-1. The small change delta x is our new tree's prediction, ft. Applying this approximation to our loss function for each data point I gives us this expression. Let's define gi as the first derivative and hi as the second derivative of the loss function, both evaluated at the previous prediction. These are just numbers we can calculate for each data point, since the previous t-1 trees are fixed. For those familiar with gradient boosting, gi is the gradient and hi is the Hessian, or the second-order information. Now we substitute the Taylor expansion into our objective. The term L of yi, y hat I at t-1 is constant with respect to ft, so we can ignore it during minimization. Let's refine our definition of a tree, ft. A tree partitions the data into t leaves. Each data point xi falls into exactly one leaf. Let's define qxi as the function that maps a data point to its leaf index, j. Each leaf j has a score or weight, wj, so the output of the tree for any data point is simply the weight of the leaf it falls into. The regularization term omega is also defined based on the tree structure. It penalizes having too many leaves, controlled by gamma, and having large leaf weights, controlled by lambda. Now let's substitute these definitions back into our approximated objective function. Instead of summing over all data points, let's group the data points by the leaf they fall into. Let ij be the set of indices of data points in leaf j. Let's simplify this by defining gj as the sum of gradients in leaf j and hj as the sum of the Hessians in leaf j. Our objective for a fixed tree structure now becomes a simple quadratic function of the leaf weights wj. To find the optimal weight wj that minimizes this objective, we can treat each leaf independently. We take the derivative with respect to wj and set it to 0. Solving for wj gives us the optimal weight for each leaf. Now that we have the optimal weight for any given leaf, let's plug this back into our objective function. This will give us a way to score the quality of a given tree structure, Q. We substitute wj star into the objective. Let's simplify the terms inside the summation. One of the hj plus lambda terms cancels out in the second part. Combining the two fractions gives us our final, beautifully simple scoring function. This score measures how good a tree structure is. A lower score is better. It considers the sum of gradients and Hessians in each leaf, as well as the regularization penalties. Now, how do we build the tree? We start with all data in a single root node and greedily add splits. To decide which split is best, we use the scoring function we just derived. Suppose we have a leaf, and we're considering splitting it into two new leaves, a left leaf and a right leaf. The gain of a split is the improvement in the objective score. It's the score of the leaf before the split, minus the score of the two new leaves after the split. Remember, our objective score is a negative quantity, so a higher gain means a better reduction in the objective. Let's write this out using our scoring function. Score before is the score of the parent leaf. Score after is the sum of the scores of the new left and right leaves. Let's try again. The gain is the objective for the parent leaf, minus the objective for the two children leaves. The term gamma is the penalty for adding a new leaf. By splitting one leaf into two, we add one leaf to the tree, so we incur a penalty of gamma. The algorithm iterates through all possible features and all possible split points, calculates the gain for each, and chooses the split with the highest gain. Let's make this concrete. Imagine we have a leaf with 4 data points. We have already calculated their GI and HI values. Let's set lambda to 1 and gamma to 0 for simplicity. First, let's calculate G and H for the parent node containing all 4 points. Now consider a potential split. Points 1 and 3 go to the left leaf, and points 2 and 4 go to the right leaf. Now let's plug these numbers into our gain formula. We calculate the score component for the left leaf, the right leaf, and the parent leaf. Finally, we combine them to get the gain. Remember, gamma is 0. The algorithm would calculate this gain for all possible splits and pick the one with the highest value. If no split has a positive gain, we stop growing the branch, and this node remains a leaf. Let's recap the key formulas we derived. We started with an additive model where we add one tree at each step. We use the Taylor approximation to simplify the objective function, which depends on the gradient gi and Hessian hi. For a fixed tree structure, this allowed us to find the optimal weight for each leaf, wj star. Plugging this back in gave us a quality score for any tree structure. And finally, we used this score to derive the gain for evaluating potential splits, which is the engine of tree construction in XGBoost. Understanding these equations reveals why XGBoost is so powerful. It uses second-order information for faster convergence, includes regularization to prevent overfitting, and has a principled way to build trees. Congratulations on working through the math behind this amazing algorithm. Thank you for learning with us today about the mathematical foundations of XGBoost.